Okay, very good morning. Welcome to one lecture. Today's one lecture is a special one. This lecture is dedicated to Professor David Newcomb, who sadly passed away this March. Dave was a professor in our department from 1989 to 1999, where he developed a vibrant research program on asphalt pavements here. He was a technical director of MnROAD pavement research facilities and started an enduring collaboration with MnDOT, which lasts today. So his work really have a long-lasting impact on the pavement research in this department. In 2000, he moved from Minnesota and became a vice president for research and technology at National Asphalt Pavement Association. Later on, he moved to his native Texas, where he was appointed as a division head of materials and payments at the Texas A&M Transportation Institute until his retirement. So now I'd like to invite Professor Mike Simmons to share a few words about Dave.
So, good morning. Many of you probably don't know me because I'm not in the asphalt area. I don't work on asphalt. I'm a retired faculty member from the environmental engineering group. And I was a close friend of David's, and I'd just like to say a few words about David. I'd like to first start off by saying this is an unusual photograph of David because he usually had a smile on his face. But anyway, I'd like to, first of all, welcome David's wife, Margot, to Minnesota. She's traveled from Texas to hear this seminar, which is going to be scintillating, I'm sure, and hold you on the edge of your seat, Margot, as it will me. So when David came to the university in the late 80s, he bought a house near me, and we were able to get together socially, and we became very good friends. Over the 10 years that he was here, we became very close. And I found him to be a caring, compassionate, and supportive friend, and the kind of friend you could count on and confide in, and I did, and he helped me through a particularly rough period in the early 90s. So he was a great friend. We never talked much about research for obvious reasons, you know, because I didn't know anything about asphalt, he didn't know much about my area. But on one occasion, I remember teasing him about his decision to go into asphalt, because to me, it seems really boring. You know, asphalt, for God's sakes. You know, but his answer to me was, oh, yeah, and you decided to go into sewage, right? So shortly after he arrived, there was a feature article, I think it was in Minnesota Daily. And this feature article had a big picture, a big photograph, and David was in the middle of Washington Avenue in the heart of the university campus with his feet either side of the center line of Washington Avenue, his arms spread out, big smile on his face. And the article, you know, they take liberties, as you probably know if you've ever been interviewed by the press. They take liberties on what you say in their interpretation. But they suggested that he was an asphalt savior. And he had come to Minnesota with his expertise to solve the pothole problem of Minnesota. And as you can imagine, as a good friend, that was like a great opportunity for me to rib him for the remainder of the time that he was here. So I would say, oh yeah, David, I hit another pothole yesterday. You know, oh, David, I broke a tire on Cedar Avenue going into a pothole. And it was all good fun. But I just wanted to say he was a really good friend. And Margot, every time I hit a pothole, I remember Dave with fondness. And with that, I'm going to turn it over to Mihai to introduce the speaker.
And thank you, Mike, for such a nice, you know, discussion about Dave and your friendship with him and Margot. So it is my pleasure to introduce our guest speaker, Dr. David Timm. I will start with the most important thing, that he actually, all his education was at the university level was done at the best university, University of Minnesota. So he has his bachelor in civil engineering, master's and PhD degrees from our university, where he worked with Dr. Newcomb's Asphalt Materials Group as an undergrad and graduate student. I have to say that he worked with many other faculty who are present here in this room. So he worked with colleagues from geomechanics and structures, Professor Ted Galambos, for example, Professor Von Voller, Boyan Guzina, and many others. So he, in 2001, he became a faculty member at Auburn University, where he became heavily involved in full-scale accelerated asphalt pavement research with the National Center of Asphalt Technology, a pavement test track. We have a very excellent test track also here in Minnesota. You probably know about MnROAD, and you had a lot of experience with MnROAD. Dave serves on the ANCAT Board of Directors, the Association of Asphalt Paving Technologies Board of Director, and is past chairman of TRB Committee on Asphalt Pavement Design and Rehabilitation. He's a very well-known and very well-respected expert in pavement engineering. And starting this year, he's also the chair of the Civil and Environmental Engineering at Auburn University. So with that, let's welcome Dave, who will tell us some very nice things about. Thank you.
Good morning, everybody. Skayuma. Skayuma. Thank you. If I try saying that at Auburn, I get a lot of blank looks and I have to explain myself, just like if I say War Eagle in this room, no one would understand what I'm talking about. Thank you, Glenn. So it indeed is an honor, and I'm deeply humbled to be speaking today. Mihai, thank you, and the department, thank you for inviting me. I'm going to try to hold it together. This is very emotional for me today. And as I was walking around the building, I was talking with some people. Some things haven't changed at all. This room looks exactly how it looked when I was a student in the mid-90s. The furniture, I think, has been updated. And some parts are brand new where I don't recognize it, but it's been wonderful to come back, and I'm just overflowing with memories of this place. And this was a very important 10 years of my life. And Mike made reference to that picture. It is an unusual picture, but I can tell you I saw that look many times. Mostly because of what I said, did, thought, or whatever I might have done just preceding that. In a room very nearby, I once had to duck out of the way of an eraser that was heading in my direction. And again, it was a well-earned projectile in my case. But it's great seeing so many familiar faces, so many people that sorry. So many people that taught me the beginnings of how to be a civil engineer. He tricked me into staying around for grad school. And when I talked to him about whether I wanted to try to pursue being a department chair, I blame him for not talking me out of it. He had an opportunity, because I basically would do just about anything that he told me to do. So for all the new gray hair that I'm generating, I blame Dr. Newcomb for that. So the title of this talk is Asphalt Pavement Design and Incomplete History, and I'll explain that it's incomplete toward the end of the talk. And what I'm going to try to do today is to highlight work that Dr. Newcomb did here, what he did at Napa, and really something that he drove home with me and all of his students was that the work needs to be impactful. It does nobody any good to spend $1 million or $10 million on something if it doesn't get into the hands of the practitioners and we're actually making changes. I'm sorry about the pothole situation. We're still working on it. But we're trying to make pavements less expensive, longer lasting, smoother, safer, all those things. We're trying to achieve that. And that he really viewed that as his core mission in academia and then working at Napa. That was his core mission, was to make things better from an infrastructure standpoint. And that was his goal. And he taught that to us every single day. And I know that that's something, some of you that were in meetings with him at the DOT That was his gospel, was make it less expensive, longer lasting, lower maintenance, safer, all those things, roll them together. What can we do from research to achieve that goal? And if we do that, we have made things better for our communities, for our state, for our region, country, and globally. So no history of pavements in Minnesota would be complete without these people, not myself, but the others. Of course, I'm going to talk mostly about Dr. Newcomb today. Some of you recognize this gentleman, Dr. Gene Skoke. He was a great mentor to many people, including Dr. Newcomb, including myself and others in the room. He was born and raised in Minnesota. He worked in many different capacities, and I had the great fortune. He came back to the university late in his career at the time when Dr. Newcomb was leaving the university, got re-engaged with the DOT. And he was a tremendous, in addition to Dr. Newcomb, he had a tremendous influence on my career. And some of you recognize Jill Thomas. She was one of, she and I and a couple other students were among 4 grad students that were in Dr. Newcomb's last class of grad students as he was on his way to Napa. And Jill, for a number of years, was the technical director and then the executive director of the Minnesota Asphalt Pavement Association. And so she has asphalt in her blood as well. But quite a number of years ago, you can tell I look a lot younger and healthier in the photo. They all came down as part of an event we were putting on at our NCAT test track. And it was such a treat to get pictures with them and especially with Dr. Skoke. I'll share another picture at another test road here in a few minutes, but it was really amazing to have those people that were so important to me come to our facility and see the things that we had going on to try to achieve those same goals that Dr. Newcomb preached every day. So I'll tell you a little bit about his career. Thank you for the introduction, and I'll kind of show you. Dr. Newcomb literally circled the country with pavements. Literally with pavements. He was born and raised in Texas, in Uvalde, Texas, and he went to school at Texas A&M, where he got his undergraduate degree and master's degree in civil engineering. He left there. His first job out of school was at the New Mexico Engineering Research Institute, NMROAD they called it. And he was doing, consulting / research there for a few years. And then he felt called to get back into academia. Somebody probably tricked him into it. I don't know. Joe Mahoney tricked him into it. Thank you, Margot. I wasn't sure if he was the one that tricked him or not, but so he went to Seattle, to the University of Washington. And when you heard Dave talk about his time there, it's like you could see him light up. It was the shining city. It was the best years of his, of his academic life were and mainly because you're a grad student. And so for the grad students in the room, shouldn't say this in front of your advisors. This is such a golden time for you. Just enjoy the people you're around, accomplish the objectives you need to accomplish, but enjoy the time that you're here because it goes by so fast and you move on to other things. And it's really a golden time. So he spent a few years there working with Joe Mahoney and on asphalt pavement things, and his dissertation is about that thick, which I find ironic because he was always upset with his students if we wrote anything that got to be too long. So I thought that to be kind of ironic that he didn't like it if it got to be too long. But he worked on pavement deflection data and back calculation methods at a time in the 1980s when our computational power isn't what we have today. And so the fact that he was doing that kind of work and running code through supercomputers, it was not as easy as we have it today, where you can run some of these codes on your phones, right? So it's a lot more accessible to people now. He loved telling stories when we would come in, as grad students would come and complain to him about 4 of us sharing a single computer. He would sit us down and he liked to use the phrase, "Let me explain something to you." I think his Texas drawl would come out, "Let me explain something to you." And he would talk about his days at Washington and probably back at A&M, where he would take his punch cards in a box. Some of you know what I'm talking about. to the library or wherever the computing center was, hand them over at 11 o'clock at night, because that's when the cheap computer time was available. And then you went home and you prayed and prayed and lit some candles that you didn't have any bugs in your code, because if there were bugs in your code and it didn't run properly, you're back the next night and your advisor's upset with you because you didn't accomplish your work in a timely fashion. He loved telling those old stories, and we loved to hear about them, as long as he then would get us a better computer. He then went for a couple of years to the University of Nevada in Reno. That was his first faculty job out of UW. And then he made a trek cross country from the desert to the frozen north to Minnesota. And that is where he began his career here. And he spent 10 years here. And in that time, he was extremely successful. He really did a lot of work engaging with the DOT. This is when MnROAD began. While he was here, he served as the Kirsten Chair of Civil Engineering, the chair that you now hold. And Miles Kirsten was the advisor to Dr. Scope before that. And so there's this just really meaningful lineage of people that are in and around this program. And so I first met him. I was trying to figure out how to stay in the Twin Cities for the summer. I had met a girl, she's sitting in the front row, and I didn't want to go back home to Wisconsin for the summer. I wanted to stay here, and I would do just about anything. I would have even worked in sewage if that was available. Anything to stay in the Twin Cities and not be driving back and forth for the summer. And so he and Dr. Mark Snyder, some of you remember him, he was the concrete professor. They posted jobs because MnROAD had just opened, and they had a need to process literally tons of material. If you went down the materials lab, there's just bags and bags and buckets full of asphalt mix, and there's concrete everywhere. And so I started working in his asphalt materials lab. And it was, at the time, it was just, I needed a job that was available. It was in civil engineering, sounds great. I don't think I interviewed very well, but he decided to take a risk on me, and the rest is part of this history, I guess. But he was very successful here, and what I'll focus on when I get done with this is some of his accomplishments and the lasting legacy, the things that he really got into the hands of practitioners that people are using today to help improve asphalt pavements. So after he tricked me into staying for for my PhD, I got about a year or two into it, and he said, all right, well, that job is done. I'm heading on to Napa. He didn't say it exactly like that, but that's how I felt at the time when my advisor came and said, well, I'm moving on. And he handled it extremely well, and it turned out to be a good experience. One of the great things that happened to me because of that, at the time I was devastated, but that got me working with Dr. Baller a lot more. I'd worked with him a little bit, but he became my sort of on-campus advisor. Dave was still involved, but I always look back and I really appreciate getting to work with Vaughn. And if you haven't had an opportunity to work with him, he's a tremendous thinker. And he taught me how to think about these asphalt problems from really a mathematical standpoint, which I really hadn't done before. And so thank you, Vaughn, for that, for stepping up and taking me under your wing when I felt like my world was coming apart. So at Napa, Dave spent about a decade there. He was the VP for Research and Technology, and he viewed that as part of his overall mission to be able to affect change on a national and even international basis. Napa has a lot of connections with associations in Europe and Australia, all over the globe. And the things that he was able to learn and disseminate, he was able to do that literally on a global scale. And there's things today that are part of his lasting legacy. And then after a decade there, it was time to move on. And so he and his family moved from Napa back home to Texas. And Texas A&M has the Texas Transportation Institute as a part of it, TTI. It's a really big research organization for civil infrastructure. And he became a division head in that organization. Very large organization. And that's where he spent the remainder of his career and retired a few years ago. And so again, I'm mostly going to focus on this kind of leg of his journey and the impact that it had. I can tell you at his memorial service and preparing for his memorial service a while ago, talking to people at each of these places, they all had the same message. He was a person that cared about people, cared about mentoring, cared about the next generation of engineers, and making sure that when his time was done in this arena, that there would not be a void or it would not be a vacuum. And I think that as academics, I think that's all what we hope to be able to do, is to be able to teach and interact and help the next generation take over when our time in the spotlight is over. So let me talk now about some technical things. So for those that are unfamiliar with pavements and specifically pavement thickness design, we can think of it on an evolutionary scale. And before the 1950s, it was really based almost exclusively on experience. You had local engineers, they mostly were geotechnical engineers. They had a general idea of their soils and the kind of environment they're dealing with. And they would know for the kind of freight they're carrying, okay, we need whatever, 5 inches of asphalt over some whatever base material over the soil, and that would probably do the job. Well, then in the 1950s, we had the Eisenhower Interstate and Defense Act, which paid for our modern day interstate system. And in classic government fashion, no offense to my DOT people, but maybe I'll say federal government fashion, they had all this money that was going to go into the interstate system. They did not have a design system. You had all these local engineers that were doing things in very different, there wasn't a national design standard. And so there was a need to have the development of some kind of a design system. If we're going to build hundreds of thousands of paved miles, we need to have some standard that we do it to. And it did not exist when that money was first made available. And so there's a big road test, and I'll talk about that in a minute, to help with that. And then in the 1980s, and this is when Dr. Newcomb comes on the scene, and some of the work that he was doing is related to mechanistic empirical, was to try to improve over the strictly empirical models where we just correlate pavement performance to particular parameters, how heavy the truck, and they're just statistical equations, they're not mechanistic, fundamental engineering mechanics type equations. And so there was a desire, and this is what we're continuing to do, is to try to develop what we call mechanistic empirical and combine those two things together. So go through some kind of fundamental computations using layered elastic theory, finite element analysis, whatever it might be, make a computation of a pavement response, and then empirically link that to expected performance, cracking, rutting, potholes, whatever it might be. In the 1990s, there was a big project that NCHRP let called 1-37A, and it was to try to develop the next generation of pavement design, what we call mechanistic empirical pavement design. And that's when I started working with Dr. Newcomb. That's what we were working on. That's what he was working on with the DOT. That was a big effort, mission focus for MnROAD, all the sensors, Dave Van Duzen, the sensors you helped install it back in the day. That was, a lot of it was devoted to trying to get a handle on this mechanistic empirical part of pavement analysis, pavement design. And now where we are is we were walking upright for a while, and now pavement designers are hunched over their computers running lots of code to try to make a prediction about what is going to happen to that pavement in the future based on conditions today. And that's where we are. And really much of Dr. Newcomb's career was wrapped up in and around this stuff. So let me talk about the AASHO Road Test. This was a project in the 1950s in north central Illinois. And I just have a few historical photos here, some primitive deflection testing. This is a nuclear density test device being hauled around in a child's wagon at the road test. Most notable for today's lecture is that Dr. Skoke was a grad student working for Dr. Kirsten, and this is him at the road test. So, and the story that Gene told me one time was his advisor said, "Hey, I heard about this road test. Why don't you go down there and see if you can make yourself useful?" And he didn't know what it was or what he was doing, and he just showed up and he made himself useful, and it became the design standard in this country for decades. And he was there on the ground gathering data, looking very sunned and fit, and with just a bit more hair back then, but not much. But he would tell a lot of great stories about that experience, and I always enjoyed hearing them. What came out of that road test was just a series of empirical equations. A good way to visualize it is to see it on a plot, and what's shown here is on the x-axis is traffic applications, the y-axis is how thick the pavement needs to be, and the lines are just design curves based on how heavy the axles are. And what's frightening, so it's a beautifully simple and it's an elegant way to design a pavement. What's frightening about it is when you see from here over at 1.1 million, that's extrapolation, and all the dashed lines are extrapolation. There's very little on this plot that we're in an empirical design system that we're working within the known sphere of information, right? So a lot of what we're doing for pavements, if we use that system, is we're extrapolating. And 1.1 million, you can get that in Minnesota on a county road in just 5 or 10 years, depending on the road and what it's hauling. And so this was a system that we used for a long time, but it's really becoming less and less relevant to what we're doing under modern traffic conditions. But one of Dr. Skoke's contributions here as part of this history lesson is that the intention from AASHO, from the road test, was that every state would develop their own customized empirical design system. The only state I'm aware of that did that was Minnesota. So if you've heard of the granular equivalency method, and I'm sure the DOT people have, maybe some of the students have, what we call the Minnesota R-value method or granular equivalencies, this is a spreadsheet you can download and use today. That happened because of the connection that Gene Skoke had at the road test, and that he took that mission seriously. He came back and said, we need to do this. And so it's a customized system for Minnesota's climate, materials, traffic, all those things. So today you can design a pavement using that. Something else that happened in the 1990s as Dr. Newcomb was getting going here was this idea that we need to really get moving towards mechanistic empirical pavement design. And the mechanistic part of it in the 1990s was a bit challenging because all of the computer codes that you would run in like an old DOS window. And so it was all command prompt. And I know the younger people maybe have never experienced this before. Some of us older people remember very well, but it would run in windows like this, and it would all be command prompt. It would say, how many layers do you want to simulate? And there's a flashing cursor. You'd hit 3, enter, and the next question comes up. What is the modulus of layer 1? And you'd enter all that stuff. And we put a short course on here for the DOT in the computer lab. I don't think anybody in this room was there, maybe. You were there? Yeah. And we used LSIM 5. That's what this program is, layer elastic analysis. And the course went great. I was just a student working as like a teacher's helper that day while Dr. Newcomb taught the course. The feedback that we got on that course was, these are all great ideas. We like the idea of mechanistic-based design. However, it's 1995. It shouldn't look like this, right? And so we went back to Dave's office a few hours later or the next day, I don't remember. And he said, well, we need a Windows-based program to do this. And I said, that sounds great. And then he said, you don't get it, do you? And I said, what do you mean? Well, you're going to create that. And I said, well, I've never taken a computer programming class. I had the computer applications class. Dr. Barnes taught it to me. We learned how to use Quattro Pro. Anybody heard of that before? A few people, not many. He'd trundle in a computer on a cart and plug it into the system, and we would take notes as he's doing things in the Quattro Pro spreadsheet. That was my knowledge of computing at that time, was that. And so he said, well, don't worry. The bookstore is nearby. Go get a few programming books and teach yourself how to do this. And I said, okay, because he told me to do it. And so I did that. I went over to the store. I bought, I think, 2 books. And so we were on quarters back then for winter quarter, whatever year. I don't know if Jenny, if you remember that, but remember the books. So we put this program together, and now that I'm in a department chair's position, I realize we should have maybe asked to use this before we just slapped it into, there's no, I don't know how many copyrights we violated in doing that. I'm sure athletics would not be happy that we didn't get permission. But we put this computer program together, and this is something that I continue to use today in my own teaching. It's basically a Windows version of what's sitting behind there. So as we got further along, and we started working together with MnDOT to put together the first mechanistic empirical method. And this might be Dr. Newcomb's greatest contribution to humanity, was the naming of this program. He very much enjoyed wordplay. He very much enjoyed a good pun when he could find it. And so when we started this program, which was born out of this program, I don't know if he was struck by lightning and that came to him or what, but we called it Rodent. And it was the first ever mechanistic empirical flexible pavement thickness design method called the Minnesota method. And we kind of started working with the DOT and what is now called, and Bruce is here. We worked together a lot on this. This is now called MnPave, and you can trace its origins. I'm not taking credit for his work, but you can kind of trace the lineage and the origins. And this is now the current design method, mechanistic empirical method that's used in Minnesota. You can trace that back to that very first short course that we taught in I guess the mid 1990s. All right. So this work, this rodent work, and we wrote a paper about it. This was the first paper that I ever got to write and submit, journal publication. It won the KB Woods Award in 2001. Which that was my first paper. I thought, oh, this is really easy. Great, every year. Well, I've never won it since, and I likely won't win it again. At the time, it was, I don't think I really understood the significance of it because it was my first time out. And so we got at TRB, we got to have our picture taken and at a ceremony, and we got to have our certificates there. There was a third author on this paper. And I'll bet if you read the title down here, you may guess who the third co-author was. He's in the room. Anyone want to hazard a guess who helped us incorporate reliability into pavement design? Dr. Galambos. He was author number 3. And when I think about that I was lead author on that paper. And at the time, it was my first paper. I thought, well, this is just how it is. And then you get into academia, you realize some people never put their students first. Sometimes the student is last or maybe not even on the paper. Something Dave very much believed in, and I know Dr. Galambos believed in as well, is making sure that the next generation was going to have a seat at the table. And one of the ways to achieve that was through authorship, who goes first, second, third. And so I'm very grateful, Ted, that you were on my committees. That was really unique. When I got to Auburn and I was interviewing, I think your name is what sealed the deal. When I was sitting down with the structures group and they asked me, oh, who do you know there, or, in the structures group? And I said, well, you were on my committee. I think that was the seal of approval that helped me get through the door. So I very much appreciate and everything that you taught me while I was here. It was in this classroom that he told me that, and the rest of my class, that if we wanted an easy job, go become a medical doctor. You're dealing with one person at a time. And if something goes wrong, it's one person. And what's the end of that story? Do you remember? If a civil engineer has a bad day, it's catastrophic, loss of life, injury, property, all those things, all the things that we know as civil engineers. It's a tremendous responsibility. I first learned that in this classroom. Thank you. He also worked me harder than I think anybody ever worked me in my life to learn structural analysis. And it's a tribute to his commitment to civil engineering education. The National Academy member is teaching an undergraduate course in structural analysis that he believes so strongly that we would learn from him. And I say that of all my teachers that I had here. It was a tremendous, just again, very important 10 years of my life spent here. All right, so let me talk about MnROAD. It was first built in 1990 to 93. If you've driven from here towards St. Cloud, you maybe have become part of that experiment as you drove over those test sections, if the test cells were open. At the time it opened, it was revolutionary. And I would say that it still is it's just so impactful, all the projects, all the renewal of it over the last 30 years. When it was first built, there was 50 test sections, $25 million in the early 1990s. And again, this is just amazing that it is run continuously for 30 years. A lot of agencies, a lot of universities are really good at getting a lot of energy and enthusiasm and support pulled together for a very short time. So projects will start and close. You might run it for just a couple of years and then things move along. The fact that it is run for 30 years is just tremendous. And I'll talk more about that in a minute. To give you a sense of the scale, there's a lot of different ways to measure it. I did a quick Google search. I found a report that Dr. Barnes had written, a MnDOT report. And in that report, he evaluated 471 million temperature records gathered from 1,300 sensors over about a 10-year period. And that's just one sensor type. There's strain gauges, pressure plates, moisture gauges. It's terabytes of information. And the job of academia is to take that data and turn it into knowledge, right? And people like Dr. Barnes and others, and Dave Newcomb certainly included, that is really the challenge, is to take all that data and turn it into knowledge that practitioners can use. If you visit MnROAD and you're going into the main building, you'll see a monument there that has some handprints, and I was lucky to get this picture. I didn't own this one, but that is Dr. Newcomb leaving his handprint. He told me when he did that, he felt it was like, a vampire touching holy water or something. His hand is going into Portland cement concrete, not asphalt concrete. So maybe that's why I didn't have the picture. Nobody in the asphalt industry had it. But that's his handprint that he was putting into that monument. And if you visit today, and I don't know, this is the handprint, and I'm not sure if somebody intentionally after his passing put those pebbles there or why that. I didn't get an explanation of it, but it's the only one that has some pebbles in it. And I'm not sure what the meaning of that is, but I took it to be significant. And so when you visit, if you happen to see that, that is Dr. Newcomb's handprint. And there was a number of very important people. Some of them are in the room today. Glenn Engstrom was really a key partner with Dave. He always talked about you that way, that you guys were co-conspirators, collaborators, partners, friends in that effort. And it is a monumental effort to keep something like that operating. And it has a very large impact. So MnROAD's been running for 30 years. I got to Auburn in the in the early 2000s, and I had nothing to do with creating this, but I've been able to reap its rewards for about 23 years. We operate a test track. We're in the deep South, and so there's a lot of laws and things that it has to be an oval, it has to be a left-hand turn. I'm kidding. But none of this dog bone shape for people in the South. It has to look like a NASCAR racetrack, basically. Okay. But it's a little bit different. We send our trucks around in circles. These guys are driving, there's 2 shifts. They run 16 hours a day. As a team in 2 years, they make 1 million laps around that facility. And you can see all the various test sections around here. They just go round and round, 26 laps an hour. We've got a lot it's really a civil engineer's playground. We've got a lot of other cool things going on. There's an erosion sediment control test facility here. We've got a national geotechnical test site here, and then up on the west curve. We've got there's an off-road course for our Baja competition team is at the site. So there's a lot of really cool stuff going on, but the heart of it, the gem, is the pavement research that we have going on. And there's a lot of things that we do there now that really predate, I'll talk about the partnership here in a second, predate the partnership, that I was able to bring with me, things that I learned from the MnDOT people, from being here, working with Dr. Newcomb, that I was able to bring and kind of implement at the test road. I also like to say that I'm part of a long-term trade. So I went south in 2001, and then Mike, what year did you come here? 2017. So it was a very long future prospect trade, but Mike was one of my PhD students that worked on the test track, and he's one of Dr. Newcomb's academic grandchildren. And I don't know if you guys ever met. You never met him, but I know that he took that academic family very seriously. And he would talk about his academic children, his academic grandchildren. He liked to trace the lineages, and Mike is of the line of Newcomb, which is a big deal. So some of the things that we do at the test track that were done at MnROAD first, putting instruments in the pavement, training, working with students, that's a big deal. FWD testing, this is out on our test road. One of the great features of it is that, you know, it's a remote location, and so we don't have to deal with live traffic, that kind of thing. Let me move on to perpetual pavements. I know I'm running short on time. Perpetual pavements, this is, of all the things that I got to work with Dr. Newcomb on, we probably worked together most on this. It's had a big impact on the industry. In 2001, he helped pull together a transportation research circular, and there was 3 authors on the lead article in this publication. From he was the lead author, and then Asphalt Institute and kind of state associations. And in it, they laid out the framework for long life pavement design, which at the time people weren't talking about. It just didn't have a lot behind it yet. And they laid out a framework in that to this notion and idea that perpetual pavements exist, and this is how we should design them. So let me first define what a perpetual pavement is. Number one, it is long lasting, so 35 years, has minimal structural improvements, resurfacing infrequently, and no deep structural distresses like you see here. We want to avoid those things. We want to avoid bottom-up cracking. We want to avoid deep structural rutting. And if we do that, we have achieved a long life or a perpetual pavement. This figure that Dr. Newcomb put together in 2001 has had a lasting impact. And in it, he describes what a typical perpetual pavement should look like, how thick it should be. If you look at the thicknesses here, if you go on the thin side, you're at about 8.5 inches. Thick side is 14 inches, so just keep that in mind. High quality material, strong pavement foundation. If you do this, you will not have deep structural problems in your pavement. It'll be long lasting. Jump forward a few years to work we were doing at the test track, and this gets into some of the reliability ideas that Dr. Galambos first taught me about, and we then got into. Was a pavement will actually experience a whole range of pavement response, just like any structure. And each curve on this plot represents a different test section at our track, and the range is just, you know, the maximum is over here, is up here, the minimums are down here, and it's just a big jumble of curves, and it's hard to make sense of it until you know if the section experienced cracking or did not experience cracking. And quite remarkably, everything on or to the left of that blue line did not experience bottom-up cracking over multiple test cycles at our track. Everything on or to the right of the red line did. And so that kind of a curve gives us a means to design a long life perpetual pavement. If we design on or to the left of this curve, we're not going to have bottom-up fatigue. And that today forms the basis of modern day flexible pavement perpetual design. So using those ideas a number of years ago, 2015, doesn't seem that long ago, but it is. We did a sensitivity analysis using those ideas. There's a lot on this table, but let's just focus on that we have kind of different sets of conditions, different climates, and so on. And if we look at the range of thicknesses here, the minimum is 8 inches. What was the minimum from Dr. Newcomb's figure? 8.5. He's within 1/2 an inch with no research behind it. And then the maximum is 15.5, and he topped out at 14. We're being a little more conservative. So 15 years goes by, lots of research, lots of study, lots of analysis, and he hit it about 90-something% correct, just based on his gut engineering sense from having been in the industry so long. It's a remarkable feat, to say the least. Today, there are the Perpetual Pavement Award Program, and they have 3 different categories of it. There's been 164 existing pavements recognized around the U.S. And the color coding, the darker the orange is, the more awards they've had. Tennessee and Minnesota are running neck and neck. Minnesota at 16 perpetual pavement awards, and that's a testament to the work by MnDOT to select materials properly, specify them properly, build the pavement to last. All those things goes into having really a lot of perpetual pavements in this state, and likewise in others. But what's remarkable about this is that it's not just in one location, right? We have them in Alaska, you have them in the Southwest, you have them in the Pacific Northwest. They're all over the country. They are not unique to a particular location. These exist, and we should design them and that's what this whole effort is to help people design long life perpetual pavements. So back to the software, it was really great that he asked me or he commanded me to go and learn how to program, because I've used it many times in my career. So Rodent, one path it went to MnPave, and the other path was now the industry standard is called PerRoad, and it was born out of Rodent. Dr. Newcomb literally wrote the book on perpetual pavements. A manual of practice was written a number of years ago, and this is disseminated all over the industry on how to design, build, maintain long life perpetual pavements. It's kind of the Bible of perpetual pavements. And after his passing, NAPA decided that they wanted to recognize his contributions in this area, wanted to name an award after him. And so this year, later this month, they'll award the first Dave Newcomb Perpetual Pavement Pioneer Award. And there's a lot of details here, but I think most notably, they're going to recognize people that left an indelible mark on the field, much like he did. And it gets into some more details here, but the things that he championed: longevity, sustainability, and superior performance. So this is to recognize people that are following in his footsteps, that have done and kind of believed in the things that he believed in. And that is a much more common photo of him with a smile on his face, except when I was in the room. All right, I'll wrapping up soon. So one of the other things that was really interesting that he kind of sucked me into was this idea that in Minnesota, other northern states, despite our best efforts, a lot of paving happens late in the season, right? This isn't January. This is probably October. I'm just kidding. Hopefully not October. But we need to have a way to understand how the conditions on the ground are changing, so that the paving crew that's used to paving in July, and they have all the time in the world to achieve compaction, that they can understand how much faster is the pavement cooling when it comes out the back of the back of the paver under the screed here. And there's a lot of things that affect it, and this idea you need to adapt the rolling operations. All the work that we do in the lab, specifying materials, all that can just disappear if we don't compact it properly. And so this was an effort that he was involved in with the DOT, this idea we need to predict the cooling rate of the mat. I know I'm at the University of Minnesota. I know I need to show at least a couple of equations, and so here they are. So we got involved, and Bruce was involved in this, I think, right? He and I were involved in this, and this was at the very beginning of me being able to program, but we tried to solve, and Dr. Voller was really the lead mathematician on this, was we had to solve a very complex problem where you have convection occurring at the surface of the pavement when it's hot and first laid. So you have all the convection, radiation, solar going on. And then through the depth of the structure, you basically have Fourier's second law, but it's going on across all these different kinds of materials. So it gets very complex in terms of the heat capacity, thermal conductivity. It's a very complex problem. And the way that he helped us solve the problem, Dr. Voller helped us solve it, was to use a finite difference moving boundary condition, and words that I never thought I would even begin to understand. And he was able to teach me. I'd never taken a heat transfer class, and I had to learn it directly from the master. And it was a really interesting project. And I'll also point out that Dave had a really unique way of disarming and making information accessible. I used to panic when I would see things like this, and maybe some of you in the room, maybe you don't panic, but you see equations like this, but he would have just a really fun way of disarming. He's like, well, that's just a couple of backward sixes. And And I don't see any upside down triangles. And so it's gonna be okay. Go talk to Dr. Voller and he'll help you solve it, right? And he just had a way of taking those really intimidating things, right? And stuff that you'd say, I can't do it. I don't know how to do it. And he'd just have a way of disarming it and allow you to work with somebody that knows how to do it, and then put together some computer code to solve the problem. And so this is just an example. If you kind of look at a set of conditions, if you look at 3 inches thick, you've laid it, and if you just look at the difference in the wind condition here from 5 mile an hour, that's this one, to 25 mile an hour, if you're on a paving crew, you lose 20 minutes just in the wind speed change. That could mean the difference between a project that meets the specification and one that doesn't, or one that makes bonus and one that doesn't. If you go from a 3-inch lift to 1.5 inches with the same wind condition, you now lose 40 minutes. It'd be nice to know that before you're out on the paving job. Maybe you have more rollers, maybe you move them closer. There's all kinds of real practical things that you can change to improve that condition. So the very first edition of this was PaveCool 3.1, and it was a Windows program, had some graphing components in here, and you feed in all this information, and it would give you a cooling curve, and it would tell you when to start rolling and when you can stop rolling, and the difference there is the amount of time you have. Years after we created PaveCool 3.1, we moved it to what we called CalCool 3.0. This was a project for Caltrans where they wanted to look at multi-lift situations. So let's say we pave it and we want to know how quickly it's going to cool, pave the next layer, and so on. And so we developed that, and from that you get a multi-layer simulation. And this should make intuitive sense that that first layer goes down, it gets down to a stop temperature, and then you place the next layer and you actually get some heating of that material as convection is taking place across that boundary. And it was just a matter of applying those basic concepts, writing up some finite difference computer code. I say it like it was easy, but it was very difficult. And this is now, we now call it multi-cool. This is now used in the industry. And we have since created, you can get it in the Google Play. Like I say this like I did this. I had a grad student do it. You can get it in the Google Play Store, mobile, web browser, Windows. But basically, what we wanted to do, and again, this is in the spirit of Dave's mission, was put that information in the hand of the engineer that's on site, that is, the snow is flying, the wind is howling. What do they need to do different so that this project doesn't have to get torn out next summer? These kinds of tools achieve that and help us achieve better, longer lasting, lower cost, more efficient use of tax dollars, all of those things. Did some validation work. And so this was some of the initial validation stuff. Bruce, I think you were involved in some, you maybe gathered some of that data. And you can see a nice match here between the predicted cooling curve in green and the measured, and then we had some information about the density as it was being compacted. We did some multi-lift validation out in California, and then this we did at our test track using temperature guns at the surface to measure the cooling rate, and it's kind of proven itself out time and again. So I guess Fourier was right when he wrote those equations. I wouldn't argue with him. I wouldn't know how to argue with him, but. All right, let me talk about the NCAT MnROAD partnership. Dave was not directly involved in this, but I think that he had a hand in helping mentor the people and work with the people that saw a need for this. And there's the monument there in the background. This is the front entrance going in there. But a number of years ago, we had a lot of very good, productive discussions and relationships between NCAT and MnROAD. A number of years ago, somebody, I don't know who it was, maybe Ben Worrell or somebody or Glenn, said, let's get together and let's see if we can put an actual partnership where we're working on things that affect the entire country, right? In the South, we have warm temperatures. Here you have cold temperatures, wet freeze, and things like that. Let's bring these together and get some national level stuff that can really move the needle in a number of different areas. And these are kind of 4 very key people to that effort, in addition to Glenn and some others. But so let me just I'll talk about the partnership test sites. This may be the only time you think of Alabama and Minnesota in the same thought. We're often on opposite sides of many different things. But in this case, we're partners in trying to tackle some really important problems. If we look at temperature data, interestingly, in the South, we actually have a low temperature in 1985 recorded at -7. This is end of days kind of stuff. I know that's just a February morning here, but for us, that's like bring your family together, buy all the toilet paper you can. This is not going to end well for anyone. Also interestingly, the high temperature on this chart is actually the northern site at 104. The conditions that you all have here are way harder to deal with from a civil infrastructure perspective. In the South, it's mostly hot, warm to hot. Here, you cover this kind of extreme is really challenging. Rainfall data, different rain conditions. The snowfall, of course, is very different. And I'll just throw this out there. This is what is actually on the ground, and this is what we imagine is happening because nobody is leaving their homes when we get a little bit of snow. So future challenges, these are all things: SMA, recycled asphalt shingles, reclaimed asphalt pavement fibers, cold in place recycling. These are all things that when Dr. Newcomb was at Napa, these were things that the industry was encountering every single day, and it was his job to figure out how do we handle these things, how do we incorporate them in an environmentally responsible way that doesn't sacrifice the performance of the pavement. He literally worked on all this stuff. The challenge that we have is how do we bring those things into programs like MnROAD and MnPave. So I mentioned at the beginning that this is an incomplete history, and it's incomplete because the story is still being written. And Dave believed very much in mentoring and working with young people, whether that was in scouting, in his private life, or professionally. But there's just so many people that could have come today and basically told the story that I told, because he had a really profound impact on people. He had a genuine interest in those around him. He had a genuine interest in helping others succeed. He was always the first person to push you into the spotlight. And for that, I am ever grateful. And I know I've run too long, Mihai, but with that, I'll close. And again, that's why it's an incomplete history, because his legacy will live on. And the things that he changed on the technical side and academia side, of course, will live on. But all these individuals that he helped influence, myself included, we're all being affected by him every single day. So thank you. And I'll be glad to answer any questions and redirect them to my professors if I can't answer them. So thank you.
We have time for a few questions. Please raise your hand. Okay.
Uh-oh.
Uh-oh.
I feel a backward
Yeah,
six
Professor Voller.
kind of question coming.
It's not going to be a backward six, but
Okay.
I was very taken with the opening of your presentation on Dave, which I thought was glorious, by the way, Dave. You did a terrific job. So if you looked at Dave's kind of academic route, it traced out an infinity sign.
Yeah, you're
And
right.
I think that's a testament to his lasting legacy, that it's going
Yeah.
to be there for pretty
Yeah.
much ever. But I just felt that was that's an observation I had that was in the mathematical framework.
Yeah, you're right.
Oh, yeah.
He literally touched all parts of our country, especially in his role at Napa. I was fortunate to, when the perpetual stuff was getting going, he and I would go out together and teach short courses to professional engineers, practitioners, and we got to spend a lot of time. And it was amazing to walk into a meeting with him that everybody instantly knew who he was, and he had instant credibility. And lucky for me, some of that credibility, I fell within the blast zone of his credibility, that it was, credibility by association. And I think others experienced that as well, is that he just had a way of bringing people together and had the technical knowledge and expertise to convince them that, whatever he's trying to convince them of, he had that at his immediate disposal.
Any other questions? Oh,
Yeah, Dave.
hold on. Just a second. Just a
The article that they did on him in the U of M Daily,
Oh, yeah.
live traffic. The reporter was up on that head bridge that's probably no longer there. And we were standing on the curb and I handed him a pressure cylinder. I said, go. And he went out there, she took a picture and I, hurry up. It was live traffic, wasn't very heavy back then. So. That's good, yeah.
That was at the start of his time here, right?
Right.
Yeah.
Okay.
Yeah. So another quick side story about the pothole. Oh, I'm sorry. Go ahead, Dr. Galambos.
Well, thank you very, very much, Dave, for whatever you said about me. It probably was beneficial, even though my hearing was incomplete. But I would like to say that with a pretty high degree of confidence that I'm the only one person here who has visited the AASHO Road Test. And the AASHO Road Test was not only about pavements, but also about bridges. And I've witnessed how the Army trucks went over a steel bridge, and as it continued after each truck, a little bit going down, until it finally collapsed. So that was one of the high
Yeah.
points of my visit there. And then my little brother, Charlie, was one of the engineers on the road test.
Is that right? Wow.
So
Amazing.
it's a great shock.
So the bridges at the road test and pavements, we call them pavement connectors, not bridges. But they were about that high off the ground, right? I mean, it was a span, but it wasn't, it was relatively low slung bridge, right? Because it was tied in with the elevation of the pavements. Yeah. Yeah, interesting.
Any more questions? Yes.
Oh,
I just want to thank Dave for what he said. You captured David perfectly. And if he were here, the first thing he'd do is insult Mike Simmons. And he would apologize about the potholes, but he would also remind you that he always considered them job security.
that's right. Yeah.
Thank you. Thank you, Margot. Any other questions? If not,
And I think the second thing he would do after this is go and talk to the young engineers in the room, ask them what you're doing and what your career plans are, and maybe try to, if you're not already in pavements, try to recruit you into pavement engineering. But he really truly believed in young people are our best hope for the future, and making sure that they're properly equipped, educated, and trained to go. And it's a big job that we have ahead of us, our infrastructure across all areas.
I
So.
can say with some security that we've never got any converts from the environmental area.
So when I took your water supply class, it was when we were on quarters. And so water supply, I don't know how it is now, but water supply and then wastewater, it was a 1-2 punch. And water supply, I was like, this is really interesting. I could see myself doing this. We went on a field trip up to where the water comes out of the Mississippi to be treated. Fantastic. I thought this could really be great. And I took class number 2 and we went to the St. Paul water treatment plant. And I thought, this isn't for me. It was impressive, really impressive engineering, but 26 million gallons a day of sewage flowing through that facility at the time. I just kept thinking, does anybody else smell that? This is really, really something. So you almost had me. Okay, thank you. Thank you.